Hello, dear students. Today we are going to discuss about a new unit by name phase rule. And this phase rule underlines that by means of a diagram, it is possible to qualitatively predict the effect of changing pressure, effect of changing temperature, and effect of change in concentration on a heterogeneous system in equilibrium. So, please note the point that this phase rule chapter deals with the behavior of heterogeneous system. I am Dr. Fazal, Department of Chemistry. And why do we need to know this chapter? This chapter introduces the concept of equilibrium between different phases of substances. That's a concept that will prove to be the greatest importance for chemical and biochemical transformations. Many of the material encountered in the everyday world in medicine, in organisms, and in the laboratory are solutions. So, it is essential to understand how a solute affects the properties of a solvent. One economically and commercially important mixture is petroleum, and the concept presented here will help you to understand how it is refined. What are the key ideas that we are discussing here? The key ideas. The dynamic equilibrium between two phases is reached when the rate of conversion between them is same in each direction. The rates are equal when the molar Gibbs free energy of the substances is the same in each phase, and therefore there is no tendency to change in the either direction. The same concept apply to the dissolving of a solute. The presence of a solute alters the entropy of the solvent and consequently affect its thermodynamic properties. Let's recall about few concepts. We know that a single substance can exist in different phases or into different physical forms. The phases of a substance include its solid, its liquid, and its gaseous form. They also include its different solid forms such as diamond and graphite phase of carbon. The carbon could exist in 46 allotropes, if you recall. Only in one case, that is the case of helium, two liquid phases are known to exist. You just inquire about it. The conversion of a substance from one phase into another, such as the melting of ice, vaporization of water, and the conversion of graphite into diamond, is what we call phase transitions. Phase transitions. The unifying concept of this chapter is equilibrium. For a given pressure, a substance undergoes a phase transition at a specific temperature, such as the change from solid to liquid at the melting temperature. More precisely, at this characteristic temperature, the solid and liquid phases of a substance are in equilibrium, at which point there is no change in Gibbs free energy, that is, delta G is equal to 0 when one phase changes into the other. Thus, even though the entropy of the system would increase if some of its melted or if it is vaporized, there is a compensating reduction in entropy of the surroundings as heat is drawn in from them. It is drawn in from them, and there is no change in total entropy of the system and its surroundings. In short, there is no thermodynamic driving force in either direction, then two phases are in equilibrium. So, this chapter is all about the dynamic equilibrium. Let's just learn. So, certain things, what do? We learn by its definition. And later we will look into what is that definition says. I want you to go for the same approach over here. So, what is phase rule? Phase rule says that if the equilibrium between any number of phases is not influenced by gravitational or electrical or magnetic forces, but is influenced by pressure, temperature, and concentration, then the number of degrees of freedom is represented by the letter F, is related to the number of components is represented by C, and the number of phases, that is P, as F, that is the degree of freedom, is equal to C minus P, that is number of component minus number of phases plus 2. So, if the equilibrium between any number of phases is not influenced by gravitational or electrical or magnetic forces, but is influenced by pressure, temperature, and concentration, then the number of degrees of freedom is related to the number of components and the number of phases by equation F is equal to C minus P plus 2. We have discussed about, we just mentioned about a particular rule, that is what we call phase rule. And in phase rule there are three important terms. Number 1, phase; number 2, component; and number 3, degrees of freedom. So the question is, what is a phase? We have just discussed about what we have seen in our daily life just a moment before. A phase may be defined as any homogeneous part of a system having all the physical and chemical properties the same throughout. A system may consist of one phase or more than one phase. It's the same what you already know, but you need to define it. That's the difficulty. So, a system containing only liquid water is one phase system. A system containing liquid water and water vapor, that is a gas, is two phase system. A system containing liquid water, water vapor, and solid ice is three phase or three phase system. So remember, a system consisting of one phase only is called a homogeneous system. So if you take glass of water, it is homogeneous system. If you take water vapor in a container, only water vapor, it is one phase. If you take a piece of ice in your hand, it is one phase system. So a system consisting of two or more phases is called heterogeneous system. So you can differentiate what is homogeneity, what is heterogeneity by using the term phase. So little more about term phase if you want. In phase rule, a uniform part of the system in the equilibrium. So you can take water, it will get evaporated. So there is water, it exists in two different phases. One is the liquid water, the other one is the vapor water. So if you take the liquid part, it's uniform, it contains the same substance, and it has got the same physical form. And a uniform part of the system in equilibrium is termed as a phase. Thus, a liquid or a solid mixture could have two or more phases. Please understand. A pure substance. So, when you say a pure substance, it has got a pure substance has got the least influence by the pressure, temperature, and some other concentration terms. The least influence, I mean, it is highly cooperating with the environment, with the room. So you are not going to make any change. Where it does exist, it is highly cooperating with the room temperature. That's why we say pure. So if you take oxygen, oxygen is pure in the atmospheric temperature. So a pure substance, it could be solid, it could be liquid, or it could be gas made of one chemical species only is considered as one phase. So understand, if you take water, if it is at 37 degrees Celsius, it will be liquid only. Right? This oxygen, benzene, in its room temperature, it will be liquid. And ice. Ice means ice could exist at a particular temperature that is below 0 degrees Celsius. So it's one phase. A mixture of gases. So if you take a mixture of gas, how many phases will be there? So gases has got a particular property is what we call homogeneity. If you make two different gases enter into a particular space, they won't be showing any heterogeneity like as we do, we like as if there is no hide and seek game. They won't be one gas will not be occupying at the corner of the container and the other gas at the middle part, nothing like that. Each gas, if you take, they'll be distributed uniformly throughout. So all gases mix freely to form homogeneous mixtures. Therefore, any mixture of gases, say it could be oxygen or nitrogen, is a one phase system. So it's one phase because of the homogeneity. Miscible liquid, the case repeats. Two completely miscible liquid yield a uniform solution. Thus, the solution of the ethanol and water is a one phase system. Non-miscible liquids. So you have to take care of this. Non-miscible means they are not miscible, they are separate. So there the homogeneity is lost, the heterogeneity is there. A mixture of two non-miscible liquid on standing form two separate layers. Hence, a mixture of chloroform and water constitutes two-phase system. Let's take aqueous solution. An aqueous solution of a solid substance such as sodium chloride or it could be sugar is uniform throughout. You can again expect the uniformity. Therefore, it is one phase system. A saturated solution of a sodium chloride in contact with excess solid sodium chloride is a two phase system because there exist means if you add a little salt into water it dissociates, it dissolves in water. If you keep adding, the solution will become saturated and the excess amount of sodium chloride you added will be settling at the bottom. So there exist two phases. One is the aqueous solution of sodium chloride and the sodium chloride solid at the bottom. Now I'm asking you a question. You could see a reaction, that is calcium carbonate dissociating into calcium oxide and carbon dioxide. How many phases are there in this system? So let's see. A mixture of solid. If you are talking about a mixture of gases, it will be uniform. There will be only one phase. We have discussed about the liquid. For example, aqueous solution, if there are two substances, if it is completely dissolved, there is homogeneity, so you can expect only one phase. But if you are talking about the mixture of solid, by definition, a phase must have throughout the same physical and chemical properties, only could be called a single phase. But solid, you can't ensure the homogeneity. That's the point. So ordinary sulfur, if you take, I'm taking your thoughts into a different direction. Ordinary sulfur, as it could occur in nature, is a mixture of monoclinic and rhombic sulfur. We are talking about the allotropes. There are these allotropes of the sulfur consist of the same chemical species but different physical properties, because they are different allotropes. Different physical properties, if you wanted to understand, you imagine about graphite and diamond. So they are chemically same but physically different. You could imagine about the strength of the diamond and graphite. Diamond is one of the strongest substance ever known occurring in the nature. Thus, the mixture of two allotropes are two phases. So this is only the hint to the question. A mixture of two or more chemical substance contains as many phases. So you have here calcium carbonate and calcium oxide. So two phases already ensured. A mixture of calcium carbonate and calcium oxide constitute two phases. And there are solid phases and one gas phases, that is carbon dioxide. So calcium carbonate is a three-phase system. Three-phase system means calcium carbonate automatically dissociates to give calcium oxide and carbon dioxide. So there is three-phase system. What do you mean by component? So just now we were discussing about phase. Please understand, it's all about the physical identity. And now we are discussing about the components. Please understand, it's all about the chemical identity. Physical identity comes into picture when we are taking a particular component. Okay? So if there is a component, then only you can talk about the phase. So let's see what is this component. A system C in the phase rule equation stands for the number of components of a system in equilibrium. The term component may be defined as the least number of independent chemical constituents, in terms of which the composition of every phase can be expressed by means of a chemical equation. Means, in chemically reactive system, the number of components is given as C is equal to N minus E, where N is the number of chemical species and E is the number of independent equations relating the concentration of N species. Let's take very few simple examples. Water system has three phases, as we have discussed: ice, water and water vapor. What is the composition? What is the chemical material of all these three phases, if you ask? It could be expressed by one individual chemical formula, that is H2O. Thus, water system has one component only. You take sulfur, it could be the allotropes, it could be the solid, it could be the liquid, or it could be the sulfur vapor. So, for all of them, there is only one chemical identity, that is sulfur. The composition of all these phases could be expressed by the sulfur. So, it has got only one component. When all the phases of the system can be expressed in terms of one chemical individual, it is designated as one component or one component system. When it comes to the mixture of substances, so how do we understand how many components are there? Remember that the chemical formula representing the composition of the phase is written on the left hand side. So you should understand when we are discussing about a mixture, how many phases are there. So the chemical formula that represent the composition of the phase will be written on the left hand side. I'll show you the example. And the rest of the chemical substituents existing independently in the system as represented by the chemical formula are placed on the right hand side. So you wanted to talk about the phase of a particular chemical formula, so the other chemicals will be written on the other side. So I'll show you with an example. The quantities of the constituents on the right, what you write on the right hand side, can be made minus, so that one will get subtracted from the other one, or zero contribution of, we can make the contribution of one substance to be nullified. That is possible. So that's how many independent, the minimum number of independent chemicals are involved. That's the question. See, here, if you take the mixture of gases, for example, oxygen and nitrogen constitute one phase only. So we were discussing about homogeneous gas. Its composition can be expressed by two chemical substances. One is oxygen and nitrogen. Hence, see here, the phase. The phase means it is gaseous mixture. What does that phase contain? Oxygen and nitrogen. You have written on the right hand side. It is XO2 plus YN2. You cannot nullify the presence of oxygen or nitrogen. So hence the mixture of oxygen and nitrogen has two components. In general, the number of components of a gaseous mixture is given by the number of individual gases present. Another example is sodium chloride solution. How many components are there? Sodium chloride, there are how many components? Two components. A solution of the sodium chloride in water is one phase system, just like we have discussed before. Its composition is NaCl H2O. Can be expressed in terms of two chemical individuals, sodium chloride and water. So the phase could be identified as aqueous solution of sodium chloride, and its components will be NaCl and H2O. So two components. Therefore, aqueous solution of sodium chloride or any other solute is a two component or two component system. Let's take saturated solution of sodium chloride. We were discussing, if it is saturated, there will be two phases. But how many components? In contact with excess of sodium chloride has two phases, namely aqueous solution and the solid sodium chloride. The composition of both the phases can be expressed in terms of two chemical individuals, NaCl and H2O. So there are actually two phases. One is the aqueous solution of sodium chloride. It could be represented by two component, as we have written before, X NaCl and YH2O. So two components. And solid sodium chloride, that also could be represented by these two components, but H2O will be nullified, that is NaCl plus 0 H2O. So only NaCl is there in the solid. So to represent all this phase together, how many components you required? You required only two, that is H2O and NaCl. Hence the saturated solution of sodium chloride or any other solute in contact with solid solute. How many components and phases are present in a system where the calcium carbonate decomposes? If you recall, how many phases are there? 3 phases are there, right? When the calcium carbonate is heated in a closed vessel, you will have this equation, that is calcium carbonate. This is what that equation, N minus E. That's how I say it. So C is equal to N minus E. So totally how many are there? How many components are there? 3 components are there. Sorry. Yeah, now 3 number of substances are there. So it has 3 phases. The composition of all these phases can be expressed in terms of any two of the 3 chemical substances in equilibrium. Let's select calcium oxide and carbon dioxide as the components. You can choose. We are choosing the right way. So phase could be, there are 3 phases. One is calcium carbonate phase. It could be represented by calcium oxide and carbon dioxide by addition. Calcium oxide could be represented by calcium carbonate minus CO2. Carbon dioxide could be represented by calcium carbonate minus CaO. So, in order to represent each phase, how many components you required? Other way it is selecting calcium carbonate and carbon dioxide as the component. The composition of the calcium carbonate is 2 component system. You can do like this also. So you have taken 3 phases, 2 different combination of the substance. You can represent all the phases with those 2 components. So it is a 2 component system. The components of the system is meant the number of chemical individuals and not any particular chemical substances by its name. Please note the point. How many components and phases are present in a system where ammonium chloride dissociates? So here you must have learned calcium carbonate, it is dissociating to calcium oxide and carbon dioxide. When you talk about the partial pressure of this equation, you only consider carbon dioxide, not calcium oxide or calcium carbonate. Whereas here you have 2 gas phases. One is HCl, the other one is NH3 when it dissociates. The system consists of 2 phases, namely solid NH4Cl and the gaseous mixture containing NH3 and HCl. The constituent NH3 and HCl, it is homogeneous, so 2 phases. The constituents of the mixture are present in the same proportion in which they are combined in the solid NH4Cl. Here you have an interesting point, that is, when 1 mole of NH4Cl dissociates, you will get 1 mole of HCl and 1 mole of NH3. That's the stoichiometry. The composition of both the phases can therefore be expressed in terms of the same chemical individual, that is NH4Cl. So, that advantage is not with the calcium carbonate. So, phase, there are 2 phases, solid and gaseous. Solid you can represent by NH4Cl, and gas also you can represent by NH4Cl. Need not be NH3 plus HCl, because they dissociate in 1:1 ratio. So only NH4Cl is more than sufficient. What is the component? It is the least number of chemical species. So thus the dissociation of ammonium chloride is a one component system. So the next term which is appeared in phase rule is degrees of freedom. The least number of variable factors, it could be concentration, pressure and temperature, which must be specified so that the remaining variables are fixed automatically and the system is completely defined. So a system, if there is no variable is required to represent a system, is known as the non-variant or having no degrees of freedom. If it is one, it could be called as univariant. If only two are there, it could be called bivariant system. So for pure gas, the degree of freedom will be 2. It need pressure and temperature. For a mixture of gases, it is 3. When it is a mixture of gas, you have to even talk about the number of moles. For water vapor, it is 1. Because when you talk about 100 degrees Celsius, you know the vapor pressure of water that is equal to the atmospheric pressure. So 100 degrees Celsius, 1 atmosphere, if you know 1 atmosphere, it is 100 degrees Celsius. So 1 is enough. So for saturated solution NaCl, if you take, what amount of substance is dissolved, the solubility. For ice water vapor system, it is triple point. Recall that, triple point. When you say triple point, it exists only at a particular temperature, pressure and concentration. You don't have to talk about any variable. It's understood. So it's a non-variant system or 0 degrees of freedom. And you already know the equation, that is PV is equal to nRT. PV is equal to nRT. So this equation says that if you know three variables, you can understand the other one. Need not be number of moles. For a given sample of any pure gases, PV is equal to RT. If the value of the pressure and the temperature be specified, if it is 1 mole of substance, I have taken n mole. Now here it is 1 mole. So volume can have only one definite value, or that the volume, the third variable, is fixed automatically. Hence the system containing a pure gas has 2 degrees of freedom. For a mixture of gases, if degrees of freedom is 3, the degrees of freedom is 3, we have already said. A system containing a mixture of 2 or more gases is completely defined when we know its composition. I said number of moles, temperature and pressure are specified. Since it is necessary to specify 3 variables to define the system completely, the mixture of gases has 3 degrees of freedom. The system water in equilibrium with water vapor has 2 variables, that is temperature and pressure. At a definite temperature, the vapor pressure of the mixture can have only one fixed value. Thus, if one variable, that is the temperature or the pressure, is known, then the other is automatically fixed. Hence, the system of water has 1 degrees of freedom. System of water 1 degrees of freedom means you consider about the melting of ice. Then if you can talk about the pressure, you know what is the temperature. If you know what is the temperature, you can understand what is the pressure. So only one variable is enough. For saturated NaCl solution, degree of freedom is equal to 1. The saturated solution of sodium chloride in equilibrium with the sodium chloride and water vapor, because it's all about the solubility. And if you know 1, that is the temperature, you can understand about the pressure. If you know the pressure, you can understand about the temperature. That define the system entirely. So it's a one component system. Thus the system is completely defined if we specify the temperature only. The other 2 variables, it could be the composition of NaCl. solution, that is the solubility, and the vapor pressure have definite value at a fixed temperature. Hence the system has 1 degrees of freedom. For ice water vapor system, the degree of freedom is equal to 0. It is non-variant system. In the system ice water vapor, the three phases coexist at a freezing point of water. Since the freezing temperature of water has a fixed value, the two variables, that is the temperature and pressure, and both these are already fixed, there being no need to specify any variable, hence it has no degrees of freedom. That's all about today. Thank you for listening to me.